Okay, so we're going to be talking a little bit now about some of the concepts Salcon covered in his Le Chatelier video. Um, so I thought we would take a look at a couple of problems. And again, just to warn you, these are MCAT level problems. So if they feel a little hard, don't freak out. Again, we're looking to challenge you and stretch your brains. Um, okay, so here we go. Nitrogen dioxide gas can be formed by the endothermic reaction shown below. Okay, so do you guys happen to remember what endothermic means versus exothermic? I always think it's helpful for my memory for me to think of them kind of together, right? Exothermic means releasing heat, versus endothermic consumes heat. And it's worth noting that when we're in equilibrium, when we're dealing with Le Chatelier's principle and equilibrium in general, any reaction that is either endothermic or exothermic on some level is both, right? Because an endothermic reaction that is consuming heat, like this one, if this side is consuming heat, if this one is endothermic, then on some level, in order to be in equilibrium, this other side of the equation has to be exothermic, right? That's how it works. In order for everything to be in equilibrium, you can't have one without the other. So they're asking you which of the following changes to equilibrium would not increase the formation of NO2, right? So which of the following would not increase the formation of, let me pick a different color, this substance here, right? Okay, well, if we increase the temperature, right? If we increase the temperature over here, if we increase the amount of heat, what's going to happen on this side? Well, guess what? We're going to have a decrease in temperature. And because this is on some level an exothermic reaction, that would mean we would be, that's right, you guessed it, creating more of this. Okay, so we've eliminated A, right? We know that an increase in temperature will actually increase the formation of NO2, and we're looking for the thing that would not increase it. Okay, well, continuing to kind of think about Le Chatelier's principle, right? We also know that adding additional N2O2 to the system is probably going to mean we're going to get an increase in NO2 overall in order to, again, maintain that balance, right? So that one we can check off. Okay, removing NO2 as it is formed. Again, if we remove it from the system, in order to balance itself out, is going to continue producing it, right? So that would also increase the formation of NO2. And that leaves us with process elimination. With B, a decrease in the volume of the container. And again, if you think about it, we know this is only with gases, right? But with gases, remember that when you decrease the size of the container, you increase pressure, right? And essentially what ends up happening in terms of our balance is that in order to sort of balance out, the side with fewer moles will get increased as compared to the side with more moles, right? So notice in this case, NO2 has more moles, so that side would actually get decreased as opposed to increased. That bears out our process elimination for B. Beautiful. Okay, so here we are again with another lovely example problem. Notice that in this case, we are again dealing with an endothermic reaction. Remember, endothermic means that this side here is exothermic, which means releasing heat. And this side here is consuming heat. So consumes heat, releases heat. Okay. So they want to know which one of the following changes would cause the equilibrium to shift to the right. So in other words, which one of the following would cause a little bit more activity over on this side of the equation? Okay, so adding neon gas to the equation. So this is a little bit of a trick question. Not going to lie to you, a little bit of a trick question. Let's see if you guys can figure out why. Think about where neon appears on the periodic table. That's right. It is a noble gas. And what do we know about noble gases? We know that they are inert, which is just what it sounds like. It means they don't interact, which means that it would make absolutely no changes to our equation. So it would not cause the equilibrium to shift to the right. Okay, removing some H2O. Okay, so if we removed some H2O, right, from this side of the equation, right, essentially what would happen is, again, the system would scramble, right, to try to put that H2O back into the system. So if anything, this would shift the equilibrium to the left rather than the right, so we can, get rid of this one as well. And then increasing the pressure. Again, we talked about this a little bit, up here a moment ago, right? But when we decrease the size of the vessel, that increases pressure. When we have increased pressure, the side with fewer moles overall is going to end up getting increased or favored. And notice that in this case, we've got 1 mole and 1 mole versus 1 mole and 3 moles. So this is still the side that would get favored rather than the right side. So that one has to go away as well. So that leaves us with increasing the temperature. Process elimination tells us that must be our answer. But logic tells us that as well, right? Because if we really think about it, well, we know that when we increase the temperature in an endothermic reaction that is consuming heat, right? Then that means that over here on this other side of the equation, we're going to have to be releasing a lot more heat in order to stay in equilibrium, right? If we increase the temperature, that would cause equilibrium to shift a little bit this way because this guy has to start overproducing in order to keep up. And that is why D is my credited response. Okay, last one, I promise, right? By now, this is hopefully getting a little bit repetitive, yeah? Okay, so notice we've got this reaction, right? And they've told us that we've got a change in heat that's negative. That would seem to indicate that we are maybe consuming heat here, right? We're looking for the thing that would cause the formation of additional NO2, right? So we want more of this stuff, right? More of this stuff here. So in order to get that, right, we have to ask ourselves, okay, well, would increasing the temperature do that? Well, if we increase the overall temperature, if we increase the amount of heat that we're putting into the system, okay, what's that going to do to the other side of the equation? That's going to cause an overall decrease of heat right, on this side. Yeah? So because this is an an endothermic reaction as opposed to an exothermic reaction, that's going to do actually the opposite of what we want it to do. So increasing the temperature doesn't work here. Adding a catalyst, haha, we already know, trick question SAT, because this equation's an equilibrium, Holmes. That's right. Adding the catalyst does nothing. Ha! And that's my dog agreeing with me, by the way, in the background. Okay. Reducing the volume of the reaction container. Okay, well, again, I know this is the third problem. So by this time, hopefully I've beat it into your head. But remember, when we reduce the size of the container, that increases pressure. And where we increase pressure, the side with fewer moles is going to benefit, is going to see the increase overall. So here the question is, okay, well, which side has fewer moles? Well, I've got, let's see, there's 1, so 3 moles on this side, 2 moles on this side. So, haha, that would indeed cause the formation of more NO2. Just to be thorough, let's check D, removing some NO. No. Again, if I remove NO, then the system's going to rush to replace it, right? But that's not necessarily going to do anything to this side of the equation. If anything, that's going to cause this side of the equation to suffer. So C is, in fact, my answer here. All right, thanks for sticking it out, kids, and I'll see you next time.